Let's write the balanced equation for each of these reactions. We're given the reactants and asked to predict the products. Part A, calcium iodide is CaI2. We can get the formula by using the charges of the ions. Calcium forms 2 positive charge ions, and iodine forms 1 negative charge ions. You can crisscross the numbers on those charges to get the ratios of how these ions combine. So again, CaI2, and we're told this is an aqueous solution. Next, mercury is Hg, nitrate is the polyatomic ion NO3. I need parentheses here because we're told that mercury has a 2 positive charge and nitrate is a polyatomic ion with a 1 negative charge. So you're going to need 2 nitrates for every mercury cation. So the formula is HgNO3, and there's 2 of them. So we need a parentheses with a 2 subscript. Nitrates are soluble. We're told this is also an aqueous solution. This is in the format of 2 compounds in aqueous solution before the reaction arrow. So what we're going to do here to predict the products is swap out the ions, the cations, or you could do the anions, get the same thing. So one of the products is going to have calcium now paired up with nitrate. And again, we'll need parentheses here because nitrate has a 1 negative charge and calcium has a 2 positive charge. It's going to lose 2 valence electrons. So we're going to need 2 nitrates to balance out the 2 positive charge on the calcium. All nitrates are soluble. You can use your solubility rules, which we give you. And then the other product is going to have mercury recombine with the iodide ion. All right, I'm not bringing the subscript over. We're told that mercury has a 2 positive charge. They're just switching. These ions are just floating around in the water, and they're going to recombine with the other compounds anion. Now halides, such as chloride, bromide, and iodide, are generally soluble, but one of the exceptions is if it's paired with mercury. So this is going to be the precipitate, and we'll indicate that with an S in parentheses. That's going to be the solid forming from the mixing of these 2 aqueous solutions. Now it's time to balance. We have 1 calcium on both sides, so they're good. We have 2 iodides on both sides, so that's good. And looks like this is already balanced. Let's move on to part B. Part B, we have aluminum metal. And we have chlorine gas. Chlorine is one of our diatomic elements. So that's Cl2. I'll put G in parentheses. Now these are 2 elements, so the only thing that can happen is for them to combine. By the way, part A, this is, we want to classify this as a double displacement, also known as a double replacement reaction. Specifically, this one is known as a precipitation reaction. Now part B, this is a combination reaction. Also known as a synthesis reaction. All right, so when we combine aluminum and chlorine, we need to use the charges on these ions. Aluminum forms 3 positive charged cations, and chloride forms 1 negative charge anions. So you can crisscross these charges, sorry, not the charges, but the numbers on the charges, to get the ratios of how they combine. So aluminum chloride is AlCl3. And that's going to be a solid. Now, aluminum chloride doesn't fit nicely into one of the 2 categories of compounds that we learned called ionic compounds or covalent compounds. It's kind of a transition between the 2. Let's balance this. We need a least common multiple of 6 for the chlorine atoms. So we can multiply the chlorines on the reactant side by 3 and the chlorines on the product side by 2. Don't forget to update the aluminum. And to rebalance the aluminum, we need a 2 in front of the aluminum on the reactant side. So there's your balance equation for the combination reaction between aluminum, metal, and chlorine gas. All right, moving on to C. We have silver metal. Silver is Ag, and we have hydrochloric acid, which is hydrogen chloride and dissolved in water. So that's AQ. This is in the format of an element and a compound before the reaction arrow. So when you have that kind of format, you need to take a look at the activity series of metals. Silver, as you might remember, is toward the bottom of the activity. It's not very reactive. We make jewelry out of silver, and gold is even less reactive, because you don't want to make jewelry out of very reactive metals. You want them to be non-reactive. So the metals toward the bottom of this list are not reactive enough to replace the metals above it. In this case, hydrogen is not a metal, but the cation above it. So this is no reaction. All right, finally, we have D. We have the combustion of acetylene gas. And it doesn't specify, but we're going to assume this is a complete combustion. So we're given the formula here of acetylene gas is C2H2. And in a combustion reaction, we need oxygen in the reactants. And in a complete combustion, we're going to have carbon dioxide and water. If you remember the shortcut method to balancing the combustion of hydrocarbons, we know that the subscript next to the H in the hydrocarbon has to be multiples of 4. So I need to put a 2 there. We can always reduce at the end. Now, this coefficient in front of the carbon dioxide has to match the number of carbons in the hydrocarbon. So that has to be a 4. Because the only place carbons show up are in the hydrocarbon and in carbon dioxide. Now, the only place hydrogens show up is in the water molecule and also the hydrocarbon. So the coefficient in front of the water molecule has to be half of the number of hydrogens in the hydrocarbon. So there's 4 there. So the coefficient here must be 2. Because it's always H2O. So 2 times 2 is 4. All right, finally, the coefficient in front of the oxygen is going to be the number of carbon atoms plus 1/4 of the number of hydrogen atoms in the hydrocarbon. And that has to do with the proportion of the O's in the carbon dioxide and O's in the water. I've already explained this in another video, so I'm just going to get to the answer here. So it's going to be 4 plus 1 is going to be 5.